We're in MAT 221, Calculus 1. This is Mrs. Johnson. This is video 3 of section 2.1, talking about the normal line to the curve. So the first thing that we needed to do here in this example is find the slope of the curve at x equals 3. But I'm actually going to find the actual point of tangency first. So I'm going to find out what is the value of this function when x equals 3. When x equals 3, the value of the function is -5. Therefore, my point of tangency is 3, -5. Now let's find the slope of the curve by using this difference quotient formula and then taking its limit as h goes towards 0. So the first thing we're going to do is we're going to put 3 plus h. Now notice the 3 came from, that's my a value here. So this is f of a plus h minus f of a over h, where a is equal to 3, where x is equal to 3. We're putting it in here. We put it into this equation, and we get 4 minus 3 plus h squared minus -5, which was f of 3, which we just found up here. F of 3 was -5. Doing a little bit of algebra here, I'm going to FOIL that binomial. I'm going to distribute the negative. I'm going to combine like terms. And then I'm going to factor out an h. I cancel those h's. And then I'm going to take the limit as h approaches 0 of -6 minus h, which equals 6 when I do a limit by substitution, which equals -6, I'm sorry. So now that we know that the slope is -6, the negative reciprocal of that slope, which would be the normal line to the curve, would be positive 1/6. The value of the curve we already found out, that was the point of tangency, was 3, -5. So writing the normal line to the curve would simply be f of x, or g of x in this case, equals slope, which is the slope of my normal line, which is 1/6, times x minus the x-coordinate, which is 3, plus the y-coordinate, which is -5. There's the equation of the tangent line, or in this case, the normal line to the curve at x equals 3. Now, can a graph have no tangent line at a given point? We're going to discover that this is true as we move forward in the course, but yes, there are points where that have no tangent line to the curve. Sometimes we can't find a tangent line to the graph at a point. For example, can we find the tangent line to the curve at x equals 2? In this particular case, at x equals 2, that bounce point of the absolute value curve, because of the sharp corner, the slope on this side of the curve on the left side and the slope on the right side actually never come to agree to each other. And if you noticed before in our examples, we had that as q came closer to p, eventually those two values would agree with each other as we come in from the left and as we come in from the right. So as a result, we can have a point where we don't have a point where the derivative exists. We'll talk a little bit about this later in the course. So reviewing what we did in section 2.1, the average slope was simply the change in y over change in x. The slope at a point was the limit of the average rate of change, or the limit of the average slope. Don't mix these up. One is the average rate of change. One is the slope at a point, because I'm taking the limit as the distance between the 2 points that we're looking at is coming closer and closer to 0. The average velocity is the total distance divided by the total time. Instantaneous velocity is the limit of that position function, that change in position over change. All right, so there we have it. There's a quick review of what we did in this lesson. Remember, velocity simply means the slope of the curve at a given instant. All right, so that ends section 2.1. We'll move on to section 2.6 next, when we talk more about the derivative as a function. Have a good day.